All right, so now we will have a panel discussion. I think everything about machine learning and particle physics and cosmology. So we'll begin the session by Partha. So Partha, can you just?
Okay, so I thank organizer because they chose this area. This is mostly newly developing area, so they chose this area for this panel discussion. So we in this session, basically me, Monalisa, and Sanmay, we three discuss some part of this development, and gradually after that we'll try to discuss if any question arise. So this is evolving field for last 10 years. So I will try to speak on the easiest part of it, or first part of it, which is basically evolution and how we can motivate this area for the particle physics and cosmology community. And then Monalisa will take up to give 2 to 3 particular example where you can demonstrate this power and how it can be useful for this purpose. And eventually Sanmay will talk about the synergy between particle physics and cosmology and how we expect the advancement in this area. Okay, so let's begin. So we all know in our everyday life we are using different applications of machine learning, and we are kind of very surprised with their capacity and their complexity every day. But what is very interesting for us as a researcher, actually dramatic shifts are also happening in almost all research fields, including healthcare, medicine, finance, education, many fields it is happening. And even more interesting thing is that several experiments in high energy, in cosmology or in astroparticle, which found their relevance, and that is by the scientific discoveries through ML driven. One of these classic example is ice cube actually. They wanted to observe high energy neutrino from the galactic object, and what happens, it is in the South Pole. You know that the string under the 1.5 kilometer ice base, below the ice base, and so basically cosmic neutrino, high energy neutrino, which comes through through this ice, and they produce this radiation that they capture through strings of detectors. So you expect handful of them in an event, and that is in that remote place. But problem was that every second you expect around 2,600 atmospheric neutrinos, which will produce similar kind of signal. So it is very difficult, not only because you have to reconstruct at that level to accept some of the events. It is even more difficult because it is a very remote place in the South Pole, and there is a limited capacity of this computation and pre-selection, and you only select those valuable events which you send to mainland. So they have actually developed a very sophisticated event reconstruction based on every pixels, and what I understand that they take a matter of hours to day to reconstruct event. So it is very extremely slow, so that's why you cannot accept most of the event. And then a few years back, one graduate student, I think in PhD work in Germany, he developed a CNN network. CNN is one of the most celebrated network which evolved most of us into the regime of deep neural network. So he has developed that one and shown that you can improve this detection technique, means time-wise, 100 to 1,000 times. So now it become possible to accept most of the events and try to see which events are more reliable or which you want to actually get. So by doing that, so they essentially, in the initial period, they were always getting their signals in 2 sigma or around that regime. So after that dramatic shift happened, now most of the events are at 5 sigma level. And so they become so confident about those events, so they also not only this timing, the angular separations or proper angular resolutions, they are 50% up also. So even with this advanced technique, so they can actually pinpoint the galactic object from where it is coming, high energy neutrino is coming. So basically they become our neutrino telescope looking at the sky. So also they started contributing in multi-messenger era. So these are the classic examples. So this is the yearly evolution. If you try to see INSPIRE HEP literature, how many are based on machine learning, from 2012 to 2024, last 12 years, it is a dramatic increase, around 90 times increase, whereas in Sensex is only 4 times. Okay, so particle physics community, we know that we have to we try to see different kind of new physics in these 3 frontiers, energy and intensity and cosmic frontiers. And also this is computational frontier which become relevant for all these different frontiers actually. So we know this these computing and methodology innovations are actually needed to get full advantage of this important data we get from these instruments. Basically, 2 of the top 10 most cited paper in all time particle physics is Giant and Pythia. They are detector simulations and HEP collision events generations basically. But interesting thing is that most of the LEP and most of the CMS and ATLAS computation resource, half of them are occupied because of this computer simulation. So there needs a significant shift, especially when you are going high luminosity. Also, not only in high energy physics community, if you look at the other frontiers, cosmic or intensity frontiers, story is essentially same. So I will start telling that machine learning is not new for the HEP community. Actually, we are using in this different low to high level experimental measurements with track finding, calorimeter, heat reconstruction or particle identification, energy or momentum reconstruction for decades actually. We mostly use this kind of high-level multivariate analysis or boosted decision tree extensively during with the primary focus for these classifiers, and it has significantly contributed in the Higgs discovery also. But today our main focus is slightly different. I will try to emphasize this emergence of modern deep learning era during this last 10 years has greatly outperformed this previous state of art actually, and they have proved to be a completely they can use actually very low level, higher dimensional input features, and they can be very powerful. They are based on these 4 driving force. So we know this when you are classify as our initial example I talked about in ice cube data, that you try to find a faint signal against large background. We try to move into the higher dimensional space and multivariate analysis with high dimensional variable you do, or you try to do low level variables from the detectors, and number of dimensions become very large. At this point, actually, these deep learning methods become very important. We try to find some kind of decision boundary or division boundary in this higher dimensional space, and and that works because we have something called universal function approximation, where it can shown or mathematically proved this neural network with single hidden layer can approximate any continuous function to any desired precision. It can be even better when you do these deep learning models where multiple hidden layers. It solves the needs of infinitely large number of nodes in a shallow network. This learning is scalable with data, and larger data gives essentially better performance, and it actually now capable of extracting features directly from the low level data, and that is very useful for our purpose. There are several kind of data we can use in this purpose. So mostly you can ask this question in this next two talks, where you will try to see that different kind of data was utilized, like time series data or image data. As I told already, image type of data, where CNN network is one of the most celebrated one for a long time. And similarly, you can use this time series data also for analyze. Also, recently there are lots of development in the area of graph neural network, where you don't need to stick to a particular structure of data input, where you can use this non-Euclidean or more kind of freely defined data structure you can give as an input. And there are lots of works use probably Sanmay will refer some of them with a point cloud and graphs. So now question is how machine learning works. So we have so many of us has pretty good idea. So it is interface between different domains actually. Not only computer science, also you need some kind of statistics and data science overlap with it, and strongly backed by this domain expertise, which is in our case this different kind of data structure and theoretical understanding. So our loosely speaking, our main purpose was to find some kind of decision boundary, which is a surface that divides multidimensional feature space into the distinct group of data points. This is done by the training, where this machine learning algorithm discovers the decision boundary through this training data. Also, once this model was constructed, that model can be used on unknown set of data, unseen set of data, to forecast for the testing. Okay, so there are three primary class of learning. One is supervised learning, another is unsupervised, and reinforcement learning. Some of the class will be discussed in the second session. Also, Sanmay will talk about that. So here I try to motivate why last 10 years suddenly it evolved, this deep neural network. Actually, this is one kind of storyline of our history. Say some challenge called ImageNet, where large scale visual recognition channels is every year held, and where this kind of image data is given with millions of training data, where you have to recognize multiple picture out of this image thing. It was seen that most of the previous, before 2012, most of the images are recognized by this feature engineering, and 2012 this deep CNN was used by this AlexNet, where it was seen a dramatic improvement over that one. And after that, actually, most of that last several years, only deep learning methods were used to improve. And not only that, typical human capability or human capacity was set at 5% level, so which was kind of crossed by 2014, and actually now since then this competition is consistently owned by deep learning convolutional networks. So not only this image classification, it also happens in different other perspective, as you have noticed that day by day, different kind of speech recognition, decision making, language processing, in every field, it actually last 10 years evolved so fast, and this is the human level capacity, and it outgrown of that. So this power is actually, you can actually use in different detectors level effects or recognition or unsupervised learning also. These are the several class of areas people work on it. These are the widely variety of class based on their representation, targets or strategies. So these are the kind of evolving area, and people are working in different classes. So I stop it here, and next talk we will take question after all three talks.
So we will take question after everyone is done. So our next panelist is Monalisa. Monalisa, please.
Okay. So first I'd like to thank the organizer for giving me the chance to speak here. Now, in the first part of the talk, what you listened was what exactly is machine learning and why it is important for the HEP community. And also you also came to know that how machine learning, or in some aspect deep learning, it has been influencing our day-to-day lives. Now in this second part of the talk, what I will do is that I will try to convince you with 3 examples. So I have taken 3 examples, and I will try to show what is the current status in these 3 examples, and how with the implementation of different deep learning methods we can actually learn what is going on or what LHC is planning there. So let's move forward. So these are the 3 things which I will be concentrating on. First part will be on the model agnostic new physics search. So we will try to understand what exactly is this thing. Then we will try to see how exactly deep learning has been implemented in the detector simulation framework, and finally we will go on to unfolding. So these are the 3 problem statements which I will be discussing here. So first, a brief introduction. So we all know, and we all have been listening since the since yesterday, that LHC is currently producing a large amount of data, and this is actually making our discovery potential for new physics enormous. But we have seen that we have not found anything till now, and what we are doing is we are giving limits. That's the current progress. But the question here we would like to ask is, what if new physics is hiding in the data, but we have still not looked at it? So probably the way we are looking at it, it's not the way you should do. So in order to illustrate this particular point, in this paper, Nachman, Kim and Kong with Whiteson, what they have done is that they actually looked at different different scenarios. First was they considered a standard model particle, they considered a new particle which was decaying into 2 standard model particles, okay, so B and C. And after that they constructed different models, and in the context of the models, what are the different final states you can get. And then they found that with these signatures, some of them have been explored at 8 TeV LHC, and the green points, they are the one which have been explored in the current 13 TeV. But you see the null points, these are the points which are not yet explored by the LHC. So these are the, like, if you have signatures with like electron and quark, or like a lepton and jet in the final state. So I would like to mention here, this paper is from 19 not 7. So probably some of this may have been seen, but you can see most of the decay channels have not yet been explored at the LHC. And now if we try to complicate this a little bit, where B and C are some BSM particles. So one BSM is decaying to another BSM and they are decaying to standard model. And if you look at that case with all the different final states you have, you will see that a lot more space is not yet explored. So this is somehow telling us that, okay, so we have to do a more model independent search. So what exactly is this model independent search? So this is a beautiful plot which has been done by in this paper, where they have seen, where they have actually, concentrated all the things. They are saying that if in the x-axis, we are saying that whenever we are trying to conduct a search, how much we are depending on our signal and how much we are depending on our background model simulation. So if you look, most of the time when we are doing our Pheno studies, we are in this part here. So what we do here is that we take the help of Pythia, we generate it, and then we do some detector simulations. We simulate our signal, we simulate our background, and we try to give some limit on that. So this is the usual scenario which people have been doing. But now, as you can see, experiments, they are trying to conduct different search ways by which you can say that signal, it should not be dependent on the signal. So this search, you can see, this is a model unspecified search in CMS. So this music in CMS and general search in Atlas, their search methods, they are more signal model independent. What it means is that it is background dependent. It means that you are simulating your background with your standard simulation packages. Then what you are doing with that, you are distributing in a bean size, you know how many events are in each bean. Then you are looking at your data, and from there you are trying to give constraint on your different new physics scenario. So that is the reason why this is signal model independent, but it is background model dependent. Then there are some searches which actually simulate your signal with your favorite simulation code. But what happens is that here they are looking at ways by which you can reconstruct your background in model independent way. So there are like various inverse selection criteria, sideband criteria, which we will discuss. So that is how they are trying to do that. And the most interesting case here is this particular approach. So here you can see some names. So what here these are. So we have autoencoders, we have anode, koala, salad. So what these are? These are different machine learning or deep learning architectures, and these architectures are designed in such a way, what they do is that they can look at the data directly. So LHC data, they are looking directly, and from there actually they can give some limit on new physics model. So that's why they are your signal model independent as well as your background model independence. That is, you do not need any Pythia, any simulation detector simulation package to simulate your entire signal background and then give the limit. So that is the thing. Similarly, they have given another plot where how you can do your background estimation in a more model independent way. So these are like, if you want, we can discuss this afterwards, or you can always go back to this paper and you can have a look how exactly these are done. So now that we have seen this, so let's try to discuss some of these architectures. What exactly are these architectures and how they are helping us to do a model independent search. So first we have the autoencoders. So what exactly are autoencoders? So you have already seen this architecture in Swagata's talk yesterday. So what you can see here is that you are giving your features. So features is like, if you have an event, you are looking at the PT of the event, you are looking at the mass, and these are the different features which you are giving. And then you are training a neural network. So this is your neural network which you have designed, and when after the training of the network, what it does is that it tries to compress your entire data you have given into a latent space. So what is a latent space? Latent space is the most simplified or minimal way in which you can describe your data. So it is trying to find out of all the features you have given, which of the features or which combination of the features that is best describing your data. So once it has found the latent space, then from the latent space it is again going back and reconstructing the same data. So you have started with x1, x2, x3, and again after the training you are getting x1 prime, x2 prime, x3 prime. Now if you have done a very good training of your data, what will happen is that you will reproduce the data as it is. So this in turn will lead you to the loss function. Loss function is checking whether you have actually determined your data in the correct way. So that will be x1 prime minus x1 say. So if you have done it in a correct way, so your loss function will be 0. It will be a smaller one. So this exact concept they have used. They said, okay, so let us train with our standard model data. Then what it will do is that your architecture will learn how to reproduce your standard model data. So once it has learned that, then when you give it to your actual data, actual LHC data, what will happen? In case if there is any signal, the loss function will be larger than what you are getting for your standard model, and then you can give a cut on this loss function, and in turn you can give some limit on your signal. So this is how your autoencoder is working. Now here you can see in this latent space, this is deterministic, like you are getting a single value here. But if this thing becomes probabilistic, then it becomes a variational autoencoder. So that's the difference here. So now that we understand this, so let us see how people have implemented this. So in this paper, they have tried to do a separation between the QCD jets and let's say between the top. So you can see here that an autoencoder which was trained on QCD jet, this is the loss function, this light gray, and the same autoencoder when it is when the top jets are given to it, you can see the loss distribution of the loss function is different. So easily you can give a cut here, and then using that cut you can actually give a limit on, if it's a new physics model, you can give a limit on that. So this is like a very simplified way of understanding how exactly your autoencoder works here. So this same approach has recently been used by Atlas. So I think yesterday you saw how autoencoder is used in real time anomalous detection, but here this is something where they have done an analysis where you can see like yesterday, here also this is your data is trained on the autoencoder, and this is the loss function, this is the loss which it is getting, and they have considered different new BSM models, and when those models are passed through the same encoder, so you can see that the loss it's different. So they have applied different cuts. So these are like the three different cuts they have applied, and with these three cuts they are trying to see whether you can give a constraint to this new physics scenario. And what they have found is that the constraint limit is actually better than what it had been obtained by Atlas by the traditional methods. So the thing, the take home message from this particular slide is that in this search, it's mainly a model independent search. You are not relying on any specific signal hypothesis, and this is an unsupervised anomaly detection, because earlier what we were doing, we were training, we were labeling our data that this is a signal, this is a background. Here we are doing no such thing. We are directly taking the data, we are training it, and then from there we are trying to interpret what exactly the signal looks like. So I think we can move. So there is another unsupervised way in which we can do, that is known as the koala bump hunt. So this is another technique by which actually you can look for new physics data like without labeling your data set. So what exactly here they are saying is that they are saying that you can always get two samples. So these are the samples where you can have a mixture of your signal and background. So what exactly is a mixture of signal and background? So let's take this simple example. So here you can see you are looking at a process, let's say proton is going and is giving W prime, then W prime is decaying to WX and something like this. So this W prime is at this mass. So you are reconstructing the mass of that. So you are getting jets, so you are reconstructing the mass here. So you can clearly see that you have a, here you will have a bump here because we are considering a W prime of 3000 GB or 3 TeV. So what you can do is that you can always, from this distribution, here let us assume that we know that our signal is concentrated in this particular area. So we can actually consider two regions. One is this signal region. This is the region, say between 2700 to 3200. So this is one region, and then we will consider two other regions which are near to the signal. So that means we have one sample. So this is a sample where your signal is dominated, and you have another samples which are the sideband, which are near to the signal but which have background as well as signal, but your background is dominated in this sample. So what it has been illustrated that if you train a classifier, you build a classifier, you build a neural network and you train it to classify between these two samples. Okay, you train it to classify between these samples using the several observables of the jet, like the PT of the jet or the subjettiness of the jet. So all these observables you give, and then you try to classify between these samples. And if you are able to build a classifier which can correctly classify between these samples 0 and 1, you can use that information to actually classify here between the signal and the background. So that's the simple interpretation they have done. They are saying that you start with mixed samples. The only condition is that in one sample the signal should be greater than the background. Means the distribution of signal and background should be different in both of the samples. And then if you can train a classifier which can actually distinguish between these samples, you can use that information from that classifier to distinguish the signal and the background in your actual data. So this is what you can see here. After classification, after classification you will have some loss function. So depending on how accurately you want to classify, if you give a cut, you can see, you can clearly distinguish the signal here. So, and if there is no signal, you will just observe some noises here. So this is your koala bump hunt. So now this was the first part where we saw that how exactly you can use it to detect some new physics in a model independent way. The second part which I will try to convince you is that why it is required in some other aspects of LHC. How much? 5 minutes, okay. So as you can see from this plot here that currently if you look at 2018, if you look at the CPU hours which is taken by Atlas, around 38% of the time was used for Monte Carlo simulation. Now if you just look at this, then you can just imagine that at the end of LHC run 3, the computational needs, they will exceed the available budget. So this is what you can see from Atlas, and you can see if they are currently in what position they are. If they try to extrapolate it, you can see the annual CPU consumption, how much is increasing as the years are going by. And if they apply a very aggressive R&D approach, then it's increasing, the slope is less, but you can see still the increase is much more. So therefore we have to think of ways by which we can do a very detector simulation which can be very fast, and also it will be very faithful. We can trust that particular simulation. So we have to think of the ways by which we can do that. So this is where we come to the deep generative models. So what is this model is telling? These models are telling that you learn the distribution of data, and then what you do, you try to generate new data from that distribution. That means you start with some simple distribution and then you try to understand what is the target distribution. Now there are different ways by which these models work. So you have GANs, so I don't have time, so I will just tell you that what is GAN. GAN is like they consist of two neural networks who are competing with each other. So one of the network is forcing the other network to learn about the distribution. So that's the way in which the GANs work. Now as you can see, this is one of the like preliminary results which NVIDIA it like published, and it asked like we have to identify which is the picture of a real person and which is the picture which has been generated by GAN. So any guess? So one is NVIDIA, according to NVIDIA, one is the picture which has been generated by GAN, and so left, right. So actually both of them are generated by GAN. So these are not real persons. This is something which a generative network, it looked at the image of different persons and it just built it. Now if I just move it to our field, then what we can say is that if currently the simulation package which we use for detector simulation is GAN4 package. Now you can see that can we directly copy that and learn the distribution of the detector simulation what we do and do it with the help of GAN. So this is exactly what has been done in the Calogan package, but there are certain things here. So the first thing is that when we look at general images, we can say, okay, this looks like a person. So we are happy with that. But when we are in our area, when we are doing, we cannot just say that, okay, this looks like the original image. We have to check that these two images, one which is generated by our standard package and the other which is generated by Calogan, both have to agree at the distribution level. So that is something which we have to agree with that. And this is where they found that Calogan is not able to do that, even though it is, generating these images at 5 orders of magnitude in computational speed. So it's like what traditional packages, our simulation packages are doing, it's 5 orders of magnitude more than that, less than that in generating the image, but it's not agreeing at the distribution level. So you can see here, it's like somehow it's not able to learn at all the voxels here. So this is what has actually led to the next step, where people are building more complicated networks. So and then this is the final status which is there. You can see that if you look at the speed, so currently Delphis is the one which gives you a fast simulation, but realism, it's not that realistic images you are getting. If you go to Gen4 simulation toolkit, you can see that it gives realistic images agreeing with what we actually see in the detector. But the thing is, in order to generate a single image, it takes a lot of time. So, and you can see these are our generative models which were based on GANs and autoencoders, and this you can see they were very fast, but it's not as par and realism with our original simulation toolkit. Recently these new methods have been developed which are based on normalizing flows, and these methods they have found that they are both fast and they also generate the images which are much more realistic. So this is now the current status which is which has been observed with the detector simulations. So I will just go from here. So this is the plot which I wanted to show you. As you can see here that if we look at the generated servers for the different particles, so for one I think this is for photon they have shown. So you can see that this is the original simulation toolkit which we are using. And if you are increasing the number of generated servers, the time which it takes to generate the servers, it's very low for Caloflow and Calogan. So that is the thing. We can see that gradually deep learning is helping us with a very fast detector simulation. So these are the plots which they have given for positron at the 3 layers of the detector. This is the Atlas detector they have tried to simulate, and this is for gamma, And finally, I will just say in 2 lines about unfolding. So unfolding is something which we do where we want to remove the detector effects, because we know detector, it has its own faults. So whenever we are trying to learn about a distribution, we would like to understand what exactly is the true distribution, not the distribution which is being sold taking into account the detector effects. So unfolding is the process by which you can actually undo all those detector effects. So there are different ways by which you can do that, and the traditional approaches which were used, they had different they had different drawbacks. They were taking a lot of time and they were very model dependent. So there are different approaches, which is the classifier based approach and density based approach, which people have been working, and they have found that omnifold is the one which actually works the best. And this can be understood. I didn't have time, so this is the plot, you just have to see. So what they have done is that they have simulated the data using 2 different particle generators. One is with Harvik, another is with Pythia. So you see, so with one they have generated these events, first with Harvik and then with Pythia, and both of these events they are passed through Delphi's detector simulation. Then they are trying to see whether with unfolding we can actually try to match the data which is simulated by both these things. So you try to think of this, that Harvik is the real LHC data and Pythia is what you are doing in your detector simulation.
Can you please
Yes. So can you just try to see whether both are agreeing or not? And here from the plot you can see that actually there is a good agreement with this omnifold jet folding jet substructure observers. So I would like to stop here and hand over to Sanmay.
Thank you, Monalisa. So our next panelist is Sanmay. Sanmay, please. Let's thank Monalisa.
Right. So if you just wanted to learn ML and wanted to see where it's been applied in high energy physics, probably here you could have stopped and be happy that you learn almost everything what you required to know about applications of machine learning in high energy physics. However, this is a mixed audience. There are astroparticle people, someone may be interested in cosmology. So I took up sort of a bit harder work, that why don't I draw a one-to-one parallel efforts between what's happening in the particle physics world versus cosmology world, and how both the communities are talking the same machine learning language. So if we understand the machine learning language, probably we can see how they're doing underlying the same statistical task in the broader sense. So I will just try to take up on from where Partha and Monalisa stopped, told you a whole lot of principles of machine learning and their applications, and will show you how other branches of physics are doing the similar things, and following that sort of trend, how these 2 different branches of physics can talk more with each other in the upcoming days through the machine learning language. Okay, so what's the broad task? If I try to summarize what's the machine learning principle, what you learned from the previous 2 talks, it's essentially we need to write an inductive bias or a nonlinear parameterized function on some data structure, and given whether your data comes with a truth label or not, you can just split up your task in different categories. It can be a supervised learning, unsupervised learning. If your label in the data are sort of noisy, you can go for semi-supervised learning or weakly supervised learning, so on and so forth. Okay, so you essentially do some minimization of loss function through some backpropagation rule. You don't need all these details in this part of talk, but just let's try to remember that given a data structure, you don't know what kind of probability distribution they are following, and we want to write down a function which will try to emulate that probability distribution. So here I have put my favorite object in experimental particle physics, which is called jet. You don't need to know what is a jet if you don't know, but let's put it this way. However, one thing to take back, these jets are essentially what is called point cloud, which means those are a set of particles. Each particles have their own features, like pt, eta, phi, and the jet itself has its energy, mass, those kind of properties. So if you think of a set, it has properties on individual elements, whereas the collection itself has its own property. Okay, so this is sort of data structure which is called graph. And nowadays, if you sign into some ML Astro sort of conference, they will tell you that you have some distributions of galaxy or galaxy clusters. They have some scattered distribution, sparse distribution in the 3D universe. And you can pick up whatever essential physics features which define the galaxy, put them as same node features, and try to find out an inductive bias on this sort of data structures. So from a machine learning perspective, if you can build a reliable method to write down functions on sets or graphs, then probably you can use the same techniques on completely two different data structures. The loss functions, of course, depends on the physics you want to do, but you can deploy the same statistical learning principle and use the power of neural networks to do similar kind of stuffs. So the whole point of these two slides is that I will try to draw some sort of parallel between what similar statistical learning tasks these two communities are trying to do, and then if they can collaborate and work in future. So I just wanted to summarize what are the different machine learning methods and dataset representations which were talked about in the last two talks. There are sort of a matrix. Now you can think that many of these options have been already followed by both HEP community and cosmology community. Now in the future, new sort of data representations are coming up. I will give you examples. In the world of machine learning, in computer science, more and more machine learning methods are coming, and of course we are pretty optimistic that we will discover new physics and come up with new physics knowledge as well. So this matrix will expand both in x-axis and y-axis. So in upcoming days, which are the new elements of this sort of cross matrix elements which we aim to fill up, where both the cosmology ML people and HEP ML people can sit down and see where these things needs to be ticked off faster. Okay, so I will cite few examples from already filled matrix. You already have heard a lot about generative models, and I will cite some examples of simulation-based inference and classification and regression tasks, few, order of 2-3 examples, just to give you a more solid and concrete example how both of them are doing the same task. Okay, right. So this correspondence of data representation and neural network methods are good to keep in mind, that not all kinds sort of architecture are suitable for all dataset representation, and that's why you have all this plethora of models. If we have just an sequence of data, you can apply a fully connected neural network. You have an image, let's apply some CNNs. Then point clouds, we have graphs and deep sets, so on and so forth. So if we deploy them, this is already probably you have heard in the last talk. Like when it started in 2015 in the HEP community, it kicked off with jet images, which is like you have bunch of energy distribution in your calorimeter. Those are like grid pixelized images. You take average image and people try to do some W versus Q city classification. Very nice. This took off in our community, and people tried to establish that from regular mass-based tagger, how the new ML-based taggers can take off. It really took off very well. Now, if we go in the same language of cosmology, what people are trying is a different physics task. they're trying that in cosmology, unlike us, where we try to gather more and more luminosity, for them, a clean image is really a piece of gold. So they have some reference CMB spectrum, and they want to reconstruct and remove some noise out of it. So they want to have a function where they will give input some noisy image and get out a clearer image. That's the sort of learning task they wanted to set up. And they did it. So this is like a CNN-based method, just like we did for our jet and particle physics task. They sort of successfully deployed for many, many examples. I can't go through all of them. And they reconstructed a CMB spectrum successfully so that they can now use a clean version of the image for more reliable physics analysis. Okay. This is something I was pretty astonished that, look at the date, 2022. What are these? Like 3D simulations of galaxies. So here I think the box is order of 100 H inverse megaparsec, and what's the whole idea is that in reality one can measure some low resolution grid size of this box in the galaxy distribution. But if they can figure out what the higher resolution box distribution of the galaxies are, more information of the physics can be extracted from the same distribution. So let's build a neural network where you give some low resolution input box and it spits out a higher resolution input box. And one could like establish that the extracted higher resolution box data giving us like equally faithful information if those higher resolutions were directly taken from the first principle simulations. So these are the sort of distributions of this quantity phi with halo mass as a function of halo mass, and this is sort of astonishing for me. Why astonishing? Because I was personally interested in same super resolution based methods in particle physics, and in like 2020 end we put out a paper which was about you have a low granularity calorimeter which has all sorts of hadrons flying by, sparse energy distribution, and we solved a problem that in presence of pileup and hadronic shower and EM shower, if this is sort of the energy distribution you have, then can you resolve two photons coming out of a neutral pion? We solved the problem using same super resolution principle. So that really attracted my mind that the kind of methods we are deploying are not very different. We can actually talk to each other in terms of the machine learning principles which we are trying out. And this is truly astonishing. So I think this sort of crosstalk should happen more and more. And I will take a few more examples to show you. So this brings me to my favorite neural network, which is graph neural network. And as was pointed out by Partha, that if you have any structureless data set, which can be the most general representation of a data set, then graph neural networks are probably the most suitable neural networks. If you have an adjacency matrix, which is like mutual connection between the data elements, then it's a graph, otherwise it's an unordered set. And you can write in general inductive bias or smooth functions both on graph and sets. If you want to know what these images mean, I can explain you in more details, but let's keep in mind that a deep set is something which doesn't use these connections, but a graph neural network is actually using this connection to learn pattern between all the data correlation sitting on all these elements. Okay, so where we use them? Well, in cosmology, they are used now sort of all galaxy cluster simulations. They are used everywhere, and they are indeed very successful, because whatever is found through their first principle simulations. GNN is sort of describing halo distributions and other property of galaxy structures using graph neural network in the same way. So you can think of this is some target versus predicted for some observable associated with galaxy structures, and GNNs are doing these things pretty well. I was quite tempted with this, that if having an access to some galaxy data lets you do some simple regression task and reconstruct, I collaborated with some of my IPMU colleagues last year and found out that line of sight velocity regression, which in general can be a non-trivial task for galaxy clusters, that can be done in sort of nice GNN based regression ways. So someone naive as me who doesn't know any cosmology could try the similar sort of task because I know how to do the GNN part. Okay, so I think this was also a nice opportunity for me to learn a little bit of cosmology. So that was fun, right? So now comes to the more concrete area where I have worked on, and I think it was really fascinating, impactful stuff. So this is about identifying how Higgs decays to a pair of heavy flavor jets, quarks, and how a QCD backgrounds like a gluon can split into a pair of heavy flavored quarks. So this is an example. In Atlas, for a particular B tagging efficiency point, I have a charm jet rejection versus light jet rejection. Oh, it's getting curtailed, but this axis is light jet rejection rate. And you can see the GN, whatever you see here, is graph neural network based methods. So they essentially have sort of best light faking, light jet rejection rates compared to deep fully connected networks. And this is for CMS, where they have all variations of particle nets, and here this direction is better, and particle net is performing best when it comes to rejecting a QCD background and identifying a Higgs decaying to a pair of charm quarks, where it's useful in order to identify the Yukawa coupling. So right now, this was used in both Atlas and CMS, a graph neural network based tagger, and you can see the upper limit on charm Yukawa coupling right now has been brought down to 10. So this is 11-ish. So this is pretty cool because we haven't seen Yukawa interaction of second generation quarks, but we are moving closer and closer to it. And this is all thanks to graph neural networks. Okay. Now a little bit about simulation based inference in cosmology and particle physics. So when I was preparing this slide, someone overlooked in my slides and said, oh, you're bringing SBI in cosmology, the expansion of universe will slow down. I really appreciate that, but that's not some bank of India, but it's simulation based inference. What's the idea? Normally, parameter inference depends on the knowledge of likelihood functions. So if we somehow can bypass the actual knowledge of likelihood functions through which we insert a lot of systematics, we can probably improve our uncertainties on the parameter estimations of the model, which we often do. So here, there are a bunch of cosmological parameters. One is obtained from likelihood-based method, and another obtained from likelihood-free method, and people are trying to see if the likelihood method and the likelihood-free methods are sort of close by to each other or not, and if these methods can be adapted for parameters fitting in cosmology. And where we use in particle physics, we are using it quite heavily these days. Even there are now Atlas analyses which have been put out. So the whole idea is that without having knowledge of the likelihood function, if we measure something and data in real life experiment, can we figure out the parameters of the Lagrangian which is driving that data pattern? So this sort of efforts are going on pretty heavily. Generative models, I won't waste time because in the previous talk you heard a lot about it. The whole idea is that I have a bunch of handful of data. I don't know which probability distributions they are following. However, I want to generate new samples from that unknown probability distribution. This is the one-liner philosophy of generative models. And there are a plethora of generative models. You were introduced to GAN, where the whole idea is that there will be an adversarial feedback from the discriminator to generator, and the generator will try to improve itself. Okay. And there are something called flow-based model, diffusion models. Let's not waste time on understanding. In 2 minutes, we won't understand anything anyway. But in cosmology, these generative models are really bringing revolution. All these hydrodynamics-based simulations, people are now trying to emulate through generative model. And they are giving results which are quite close to the current n-body simulations. So that's why I made the header that this universe doesn't exist, which means it's just a generated model of the galaxy distribution, and they are sort of reliable. It's sort of the same, this person doesn't exist, all those fake images of people. So you can think there is some grand fake image of universe from which these distributions are drawn, and they're showing reliable patterns from what we learned from first principle cosmology. And in our particle physics simulation, they're really bringing revolution. They're part of the main experimental simulations. Why? First of all, look at the speed gain. Like what we do from Gian4, as the energy of the particles keep increasing, the simulation time increases exponentially. Whereas the time taken by all these generative models, they sort of flat on the logarithmic scale. And if you go to this paper and see the distributions, you really don't lose any performance on single particle resolution, let's say diphoton invariant mass resolution and things like that. So they are truly useful. And even people are trying to sort of predicting shape coming out of a differential cross section for different processes coming from the generative models. So producing realistic simulations, both in high energy physics and cosmology, that's where generative models are playing a huge sort of role, and this is really first-hand gain out of machine learning world. Okay, so I will finish my part with 2 examples what are coming out as next frontiers. One is differentiable programming, where the whole point is we have a causal flow chain, we have simulation which should be passing through detector simulations, and I have an objective function, and then there is a reverse feedback. So in terms of latent space parameter, the choice of geometry in a detector simulation, whatever is the detector and parameterization systematics, etc., all of this can be tuned simultaneously to improve the final objective. And there one can say which parts I'm going to vary simultaneously to reach the final objective function. So I can differentiate everywhere the parameters appearing in this blue box to get the best of the performances. So this is where the whole idea of differentiable programming comes into play, that if the final objective can be written as a function of all the intermediate steps, and if you know how to automatically compute the differentials for each of the steps, there are ways to optimize the final objectives. And the whole world of differential programming is using it. So where we are still lacking, we are lacking in terms of explainability, and there are efforts, there are different methods. I gave it an example for a graph, there are correlation among the nodes where we talk of GNN explainability, then there are probabilistic methods of something called PG explainer. But that's somewhere we are truly lacking, that given some learned pattern on a data set, after the training is done, how do we correlate the learned feature and the weight parameters with the physics which I'm trying to learn? So people are trying out with day in, day out different methods. I mean, we have things like Shapley values and things like that from older times, but new methods are being tried every day and these days. So that's sort of one direction. Another is reliable systematics out of a neural network. So we have methods like Bayesian networks and other, but like let's say we have done a training on a finite sample and we want to use it for inferring some variable. Now, how do we estimate the uncertainty on that estimated variable just coming out of a neural network? That's sort of a big open question which we really need to understand. We all draw ROC curves when we do classification. We never draw uncertainty bands on the ROC curves. We really need to come up with those. Okay. And finally, this is sort of all the methods right now available, and new methods are tried every day and out. So we need to see how much of this we can exploit in our physics program. And what's growing up in the next frontiers? Graph is not the final frontiers. There are new methods of topological neural network where there are methods of hypergraph and combinatorial complex, etc. coming up. And we have already tried hypergraph-based methods, which seems to perform better for particle physics, collider experiment sort of stuff. So I'm sure this sort of data structure with more higher order interconnection can capture the physics, complex physics which is lying inside the data set, and we can exploit them. Okay, and another example that when we talk of next frontiers, we in general try to implement the nonlinearity in a neural network through multi-layered perceptron, sort of universal approximation theorems. But these days, based on theorems on representations theories, people have proposed new Kolmogorov-Arnold network, which promises you to give a better explainability, but that has not been well established. So it's worth trying them out. Okay. So so I walked you through all possible examples where sort of both the HEP and cosmology worlds are doing same things in terms of machine learning, and I tried to point you out where the immediate emphasis are given for the future tasks. So we need to see if we can learn this sort of machine learning tools. Both the HEP and cosmology group can sit together and try to see if we can do something better. So that's it from my side. Yeah.
Thank you, Sanmay. So I think we can take a few questions. So I would request all the panelists to come here so that you can get the coverage of this. So any questions? You can come here so that it should be in the field view. Oh, I have been asked for him to. Oh, yeah. So any questions, comments?
Yeah, sorry, this is I don't know if the question makes sense, but let me ask. Suppose you have an image which is made up of truly diffuse photons versus an image which is made up of photons which are coming from point sources, right? So this is actually a real life problem of the Fermi galactic spectrum, where we see excess of 2 GeV photons. We do not know whether it comes from dark matter, which is truly diffuse, or it comes from pulsars, which is point-like, but they are looking as diffuse, right? So, what is the best ML idea to tackle this problem? This is an image reconstruction problem.
Set it up as a CNN problem, but inject your point-like sources for one sort of physics versus other in the loss function, where there are methods of per pixel loss functions called YOLO loss function. This is sort of an acronym, but there are ways to detect like per pixel loss functions to see if it's a diffuse from a point source or it's truly an extended image or not. And this has been tried out in the literature of like CNNs, mostly in the cases of medical image analysis. And we also have seen these super resolution things and UNet architectures for analyzing those sorts of data. So I think it's a very doable problem as long as you have a reliable training data set which can be set up.
Thanks.
Any other question?
Another question. So, for somebody, some students, postdocs who really want to get into this, at this point, what are the first concrete steps that they should take?
They should, in the morning, they should try some coding, and in the evening, they should learn some linear algebra. So, no, the jokes apart, I think by now there are very good lecture courses both on YouTube and online available codes which are available. Of course, we can link it to anyone who is interested. We organized 2 schools in India, one in ICTS and IOP, things like that. So we tried our best to make the lecture notes and the codes as good as possible for a starting graduating student here. So I think the materials are available. One just needs to try them out, and of course we are open to help them.
It's a very nice question. What is deep about it?
Deep, you have multiple nonlinear layers. That's what determines the depth of a network.
Yeah, that was there even in any neural network
Of course,
thing.
this is not new. I mean, neural networks and...
So why what is the revolution? Why it is called a revolution?
No, the revolution is about designing each individual layer smartly. Like those are smart construction of mathematical functions. And of course, the other revolution is the autograd in the neural network softwares, because each time you write a complex nonlinear function, you need to know how to take a derivative, because you will do a back propagation and decrease the loss. And if you have a complex network and if you have to do it on pen and paper, then you are lost. So
well,
there is
I did it in 90s, okay, the same thing.
No. In the 90s, when even there are videos of Jan LeCun, he was solving the derivatives by hand and implementing on the computer. So he became immortal because of those efforts. He was much ahead of time. But now you can just define the autograd function and it will do automatically. So that's the revolution, I would say.
I think the word revolution in these neural networks, it came with this ImageNet competition, which Partha was told. So before, Sanmay told, Jan LeCun was doing the accuracy which he was getting to classify between different images, it was around I don't remember, around 30%, so 35%. But gradually with these deep networks, now it has reduced that the way in which you can classify, it's around 98%. It is as per human level by which you can classify different images of 1,000 data objects.
Well, I think improving efficiency is not a revolution.
Sorry?
Improving an efficiency is not a revolution. Revolution is, if you really define a new method for doing it.
No, but from an industry standard, you may have a different...
Okay, this is industry, okay?
Of course.
It's not academics.
I mean, the boundary is phasing out these days, but that's a philosophical discussion anyway.
I think we should stop here.
No, if there are some urgent questions...
I think we are almost at the time of dinner, so we can discuss...
No, there is Sridhar's talk, no?
So this is from 7:30, right?
Oh, 7 o'clock. So
we are already 10 minutes late. Sorry.
Okay.
Sorry, absolutely sorry for that. So let's conclude here. So let's
Thank
thank all the panelists.